I'm glad you all made to this building. I know it's a little bit tough to navigate in China. So let me first introduce you the general code. Oh, by the way, I'm Wenren Xu. Also part of the team of chairing this conference. Let me first introduce you to Professor Lu Dongming, who is a professor in Zhejiang University. He leads the Institute of Artificial Intelligence in the Department of Computer Science. So, Professor Lu.
Okay, Professor Yao and colleagues and ladies and gentlemen, good morning. On behalf of Zhejiang University, I'm very grateful and pleased to welcome you to the 8th IEEE International Conference on Distributed Computing in Sensor Systems. The first discourse was initiated by Professor John Lewis and was held in Marina del Rey, California in July 2005. Up to last year, 3 successful discourses have been held in Europe and United States. The past 7 discourse conferences have featured very high quality research papers and interesting invite and contribute papers. Following this good traditional discourse, 2012 is intended to cover several aspects of distributed computing in sensor systems, such as high-level attributions and models, systematic design methodologies, single and information processing, algorithms, and applications. Besides the inherited wonderful tradition of discourse, this conference is quite special because this is the first discourse here in China, especially in Hangzhou, in our university. You know, China has not very dedicated to the promote Internet of Things. As you know, in the 2009, the Chinese Premier Minister Wen Jiabao promotes the contribution of Sensing China, smart grid, and intelligent cities. We are dedicated to see so many experts in sensor network come from around the world here to share your knowledge about the Internet of Things with us. At the same time, it's also a good opportunity for the colleague from China to show our work in these exciting fields. I hope this conference will be memorable and high educational and not to be missed events. And hope the conference will help you to become better informed about the latest trend in sensor system. Also will know more about our university, know more Hangzhou. Thank you for your participating and support for the conference. I hope you will enjoy this conference. You enjoy your lab in Hangzhou. Thank you.
Thank you, Professor Wu. I just talked with Yabo, who told me that their smaller room upstairs was taken by Professor Wu for another conference. So you feel like you have too much space, blame Professor Wu. Okay, so next, many of you may be curious how the review process goes. So I would like to invite the technical program chair, Mike Roba. Sorry, if I pronounce it horrible, right? To introduce the review process.
All right, so good morning, everyone. This year for DCOSS, we received 100 submissions to the 3 tracks that we have in this conference. Those tracks are the Algorithms and Analysis track, Signal Processing and Information Theory track, and Systems and Applications track. And I think having these 3 tracks is one of the real strengths of DCOSS, in the sense that it brings together people working in these 3 different areas of sensor networks and cyber physical systems and Internet of Things, brings them all together to exchange ideas and to discuss problems, each with their own perspective. So for each of the 100 papers that we received, we solicited at least 3 reviews. In many cases, we obtained more than 3 reviews. And based on the input that we got from the reviewers and the technical program committee members, we narrowed it down and accepted 34 of those papers. And so those are the papers that will form the outstanding program of this year's conference. In contrast to the past few DCOSS's where the program has been organized by these 3 different tracks, this year we decided to take a slightly different approach. We noticed that there were many trends across the 3 tracks in terms of the topics that kept on coming up. Things like mobility, multimedia and camera networks, as well as more traditional topics in this area like image processing or routing and MAC algorithms. Is this not on? Hello, can you hear me? Testing, 1, 2. Hey, that's better. Okay. Should I start over? No, I won't start over. All right. So we have 34 papers, and rather than organize by the few tracks that they were submitted to, we decided to organize them according to these topics. So we may have systems and applications and algorithms and signal processing perspectives all intermixed within the same track. Hopefully that will make for interesting discussion and exchange of ideas during the conference. In addition to the technical program, we have 2 excellent keynote speakers this year, Professor Kang Yao from UCLA and Professor Ivan Stojmenovic from University of Ottawa. We also have a work in progress session, a poster session, and a demo session, a panel discussion on funding opportunities in this area, and there will be 3 workshops held on Friday. We also have 2 Best Paper Awards. Those aren't going to be announced now. We have a Best Paper Award for the conference and a Best Student Paper Award. Those will be announced tonight at the banquet, so make sure that you're there to hear about that exciting information. And finally, I'd just like to close by thanking Professors Liu, Professor Wang, and Professor Xu for the general co-chairs for their help with organizing, especially thanks to the local organizers for making all the arrangements so that we can have the conference here. Thanks to the TPC vice chairs, that's Yanmin Zhu, Jia Gao, and Carlo Fischione. There was 1 track chair for each of the tracks that we have. They did a huge amount of work to solicit these reviews, get TPC members on board, and make this process go very smoothly. And I would also like to thank all the TPC members, reviewers, all the other conference organizers, and especially the authors who are here today to present this. You're going to make it a really outstanding conference. So with that, I wish you an outstanding DCOSS for this year.
Well, thank you, Mike. This year, we're very honored to have Professor Kang Yao as our keynote speaker. Professor Yao has asked me to keep the introduction short, so I'll try that. Professor Yao has received his PhD in Electrical Engineering Department at Princeton University. Currently, he is a distinguished professor in the WE department at UCLA. He has co-authored several well-received books, including High Performance VLSI Signal Processing, the book Detection and Estimation for Communication and Radar System. If you haven't read it, go home and read it. Dr. Yao is an IEEE Life Fellow, and so I want to tell you a little bit about what I learned from dinner. Aside from his academic achievement, Professor Yao is also very passionate in cuisine, food, and good place to visit. And he actually mentioned that one of his favorite comments I like is he said, most of people know Beijing and Shanghai about China, but only sophisticated people know Hangzhou. So congratulations, welcome to the club of the sophisticated people. Without further ado, please join me in welcome Professor Yao.
Connection problem with my iMac and with my MacBook Pro, so I had to take it my memory stick to see that. Okay, so it'll be okay. Is there a space for my own controller? Is there another memory stick? Windows 7 in the Mac system that are not 100% identical to a regular Windows 7. Okay, let's see. Well, let's see. Okay, works. Let's go to, how do you go to the full view? So I cannot read the command in Chinese under the Windows. Right, okay, good. All right, thank you. Sorry for the slight delay. I've been working with acoustic beamforming for the last 15, 17 years. And so that in this talk, we'll talk about our experiences with beamforming for directional arrival and localization sensor network. So I'm essentially a physical layer and sensing guy in sensor network. Sensor network, as you know, is a very broad area. This is, I'm more or less a physical layer. It is a outline of the talk. First we will have a brief introduction to beamforming. Then our experience using beamforming in 6 projects in the last 15, 17 years. Then we introduced what we call approximate maximum likelihood AML algorithm for high performance acoustic beamforming to perform detection, localization, signal interference, noise enhancement, source separation, and source tracking. We will discuss various simulations, practical field measurement data, and 2 sound demonstration illustrating the usefulness of acoustic beamforming. In this presentation, we present the evolution of our own experiences in 6 projects, as we said before, using acoustic and seismic arrays and related wireless sensor system. Beamforming in arrays can achieve detection. It can declare the presence of one or more acoustic or seismic source, and it can increase the signal interference noise ratio by enhancing the desired signal and or reject or reduce unwanted signal or noise. It can localize one or more sources by finding the direction of arrival and the crossbear in the far field. In the far field, you do not have curvature information. But in the near field, you do have curvature information, so you can find both the range and the direction of arrival. It can separate 2 spatial distributed sources, and we have a demonstration of that a little later. You can classify the sources based on spectrogram or hidden Markov model methods. You can track one or more sources by using common or extended common filtering or particle filtering methods, which we have example. Okay, the first example using beamforming, we worked on a smart hearing aid. In other words, using multiple microphones. Then acoustic array has been used to steer cameras for given speakers in a teleconference applications. There are actually commercial products already available using this method. It can detect, localize, and track hidden speakers in home security, military surveillance applications. It can detect, locate, track moving vehicles in civilian military applications. It can studies, and we're actually working with people in the biocomplexity department at UCLA with birds and animals. All right, so here is a very elementary high school level description of narrowband beamforming. Suppose you have a source narrowband. Of course, the narrowest of all possible signal is just a sine wave. And suppose you have R microphone or sensors, and they are separated at different distances from the source. So depending on the propagation delay, of course, sound wave will arrive at the microphone or sensors with a different time delay. So the purpose of a coherent beamformer is to, say, relative to the first sensor, which say has 0 delay, the others are delayed so that they're in phase. And then they're combined to give you a higher signal. Right? That's the simplest high school explanation. Of course, for a single frequency of tone, time delay can be achieved by using phase control. For wideband signal, time delay is the appropriate thing to do, but phase delay would not work because phase delay won't work for single frequency. Now, wideband beamformer, at least the simplistic level, is for each microphone input, each sensor input, you essentially have a FIR filter with different filter weights in which you can, by using appropriate complex coefficients, you can perform a time delay for the whole wideband signal, and so you can combine them together. There are many different ways of obtaining these coefficients. The first method that we worked on about 15, 17 years ago was as a front end for a smart hearing aid applications. This was actually a pre-proposal we worked on with some people. Unfortunately, we did not get funded, so the people we worked with lost interest. But we did enough work to describe. So we proposed a user-steerable, non-adaptive array that collects the maximum energy of a desired signal source called a desired directional variable and low gain called an unwanted directional variable. So you have two speakers. So the weight of the beamformer, these beamformer weights, are obtained as a solution of a generalized eigenvalue problem. There are various parameters that are used to, if you do not do equalizations in the frequency domain, the solution will have a natural tendency to enhance the high frequency signal, and so the quality of your signal would not be so good. So we actually have to do various things to enhance the lower frequency to compensate, to do equalization. Okay, we work with House ES Institute, which is a well-known hearing research, nonprofit hearing research in Los Angeles. This is a front-end breadboard built by the people at House ES Institute. So we have 4 microphones in the back here, and we were initially ambitious to possibly even put microphone in the vertical direction. So having 4 microphones in horizontal directions only control the azimuth angle. Having the vertical ones allows you also to perform elevation angle control. But we never got to that part. So this was breadboarded, and we actually performed the following experiment. So in which I have 6 cases which I'd like to show you. The first 3 cases consist of 2 humans talking, one at 0 degree, one at 30 degrees, both of them at the same signal to noise ratio. So both of them sounds about the same. In the first case, you have just in free space, if you have a single microphone, you hear both people talking. Okay. In the second case, we have our beamformer, this beamformer, using this algorithm to perform array processing, and we obtain a signal interference ratio improvement of 22 dB. Since the two signals are the same, the signal interference ratio of the interferer, the second speaker and the first one is the same, so it has 0 dB. So we gain 22 dB. In the third case, we have the same situation, except we're in a low-medium reverberation room, in which our signal interference noise improvement was only 12 dB, and we're still able to hear. Then I'll describe the second case, in which, as I'll give some demonstration in a minute. Since this was quite successful, we decided to be more ambitious, in which in the second case, cases 4, 5, and 6, we have a given speaker at 0 degree. We have the interference now is not a human speech, but it's a colored noise having the same spectral properties as a human speech, in which the noise is 10 times stronger. So the signal interference ratio now is minus 10 dB. So in the first case, with a single microphone, you're barely able to hear the speaker. With the beamforming array working, we get 21 dB, and so you can hear the speaker quite well. And in the last case 6, you are in a low, medium reverberation room, and we get only 12 dB. So we still can pull out the signal, but definitely not at very high fidelity. It's not your hi-fi system. All right, now let me see. Okay, so sound one is two people talking at the same time, one coming at 0 degree and one coming at 30 degrees. So you get two people talking. Oh, could we turn on the sound on this? Yes, I think the sound is not turned on. Sorry for these little minor glitches. Try it again. Two people talking. Go to the second case. So the second case with the beamformer working, you're supposed to hear only one person talking.
A boy fell from the window. The light helped her husband. Big dog seemed dangerous. Her shoes were very dirty. The player lost his shoe.
So if you listen carefully, you do have some leakage from the second speaker, but you can certainly obtain what the person is saying. In the third case, it's a more realistic low, medium reverberant room. The second case is essentially in free space. There's no reverberation found. Ceilings. So. Oops. Oops. It's pretty simple.
A boy fell from the window. The light helped her husband. Big dog seemed dangerous. Her shoes were very dirty. The player lost his shoe.
Well, we can still hear. The quality is not as good as the second case, okay, but it's intelligible. Okay, now the more interesting third case, sound 4, is the case in which the interferer is a colored Gaussian noise 10 dB stronger than the side speaker. Now let's see what beamformer can do.
A boy fell from the window. The light counter has big dogs in English. Her shoes were very dirty. The player lost his shoes.
Well, that's intelligent, right? It's not your hi-fi system, so you wouldn't want to listen to this on a long period. Okay, but that's in free space, in which we literally form a beam, well, at a given gain called the desired speaker, and we try to cancel out. There's only 4 microphones, but this is, if you have more microphones, you can do better, and so forth. It's only with 4 microphones, we are trying to reduce the color noise. Great. We did the case slide, so let's do the.
A boy fell from the window. The light counter has big dogs in English. Her shoes were very dirty. The player lost his shoes.
All right, so this is a case in which way reverberation. In reverberant room, the fact that we try to reduce the sound from -50 degrees, but then because of from the other reverberation, the signal coming from other directions, and those parts we had to live with. So, all right, so that was, so we were happy with that, and we proposed and so forth, but NIH didn't want to give us any money, so that was the end of that project. HEI people lost interest as soon as we did not get funded. That is unfortunate. Let's see, how do I get back to the full screen? Sorry. Let's switch over these. Okay, good. Thank you. Okay. A few years after that, we were funded by DARPA on what we call randomly placed sensors for space-time wideband frequency beamforming. So in this cartoon, we assume there are 2 sources. We have 3 different microphones. And again, this is a generic wideband beamformer. You feed the appropriate weight, and then you can, in this beamformer, we do not know the locations of the microphone or the sensors. Okay. This being a DARPA project, they assume these things can be thrown out of a truck, out of the arbitrary place. And we still want to do coherent beamforming. Okay. So the algorithm we use is, okay, here's the usual statement value, collect auto and cross-correlation information, you feed into one giant matrix. You solve another eigenvalue problem in which the eigenvector corresponding to the largest eigenvalue would then be used as the coefficient. So in this example, we assume there are 3 of them. So each one of these has L taps. So we have 3 L coefficients we need to find. So we packed all this. So this is a matrix eigenvalue problem in which the eigenvector is of length 3L. So the first L of them goes to the first beamformer, the second, the third. So, and the result we use is based upon Zago's theorem, which is a Hungarian mathematician who emigrated to America in the 1930s as a professor at Stanford University for many years. And this result was the 1920s. So even though we claim this stuff is modern, but the mathematics we use is old, which is not surprising, appeared in a journal a couple of years ago. And so using this algorithm, the beamformer actually automatically steers to the strongest signal and do whatever reduction it will to the second source. And this is not necessarily needing to know the placement of the microphone. Okay, so that's why it will be applicable. Unfortunately, this is not distributed processing. We have to get all of the data together to perform this eigenvalue. So it's not meeting the criteria of your conference, which is distributed processing, but a later method which I described is better than this one is. So at least I'm not being dishonest in presenting this keynote speech to a distributed processing sensor network conference. Okay, so now we also can find the location of these guys. Now, to find location of, if I need to find out where you are, you must have some coordinate system. Otherwise, how can I tell you where you are? So in that case now, we assume the locations of the sensor now assumed to be known. Otherwise, we cannot do localization. Right? Otherwise, what does it mean I know where you are without having some kind of coordinate system? We assume the first sensor is sitting at x1, y1, z1, and 0, 0, 0. Okay. And then the others are x2, y2, z2, up to, we can have n of these microphones up to xn, y, and zn. So we actually know the position of the microphone. The method can estimate the time delays. So these are the time delays we can estimate. And we then just solve this linear system of equation overdetermined, in which the A matrix are things that are known. Our unknown are the location of the strongest the source, which we denote by x of t for target, y of t, and z of t. We actually also can estimate the speed of propagation. From your freshman physics, you know distance is equal to velocity times time. So we can estimate the time delay. Okay, so, but then you must obtain also the speed of propagation. Speed of propagation of sound in air is approximately known, but it's a function of temperature, the second order effect. But this method also applies to seismic wave. And so the propagation of a seismic wave depends tremendously on the materials. The propagation on the wood is very different than over metal. Very different. And very different from this carpet, okay, or over the aluminum floor, which you have. So we actually have to estimate the velocity of propagation. That's part of our unknown. And the V is the range of from the central coordinate system of the sensor. So A is known, B is known, so W is the unknown. So we can solve that. Okay, this was the geophone. So this is actually the theory behind the geophone and microphone is essentially the same, other than the vibration. These are much lower frequencies. So there's a geophone, inexpensive, $10 per geophone, sitting on the bottom of this box. This is supposed to be wireless. We work with Rockwell Science Center people. My group was responsible for the algorithm and stuff, and they were responsible for the wireless. They had a hard time getting the wireless working. Early days of sensor networks, what was wireless was always a problem. Okay, we performed an experiment. We have 4 of these boxes placed in the hallway in front of our department chairman's office, and we had the heaviest member of our group stomping on the floor, trying doing a straight line, just bang, 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 and these are the results of estimated location. More interesting, we also estimated the velocity of propagation about something like 3,500 feet per second. The sound is, of course, roughly 1,000 feet per second. So this is over the aluminum floor. Similar to the aluminum, same as those things you have on the floor around here. That's a standard. 1 square foot of aluminum pipe of the 1970, 80, 90 vintage medium quality office building stuff. All right, so we're able to estimate this thing. So our joke was that if our terrorists capture our chairman, then the rest of the people with this thing can find out where people are and so the rest of the people. I'm not sure our chairman appreciated that joke. All right, so that project lasted for about 2.5 years. Various wireless units were built by other people in our project. I mean, by other people, not ourselves. Okay, then about 2 or 3 years later, we had another DARPA project in which we decided this this method was sort of nice and so forth, but it really is not too realistic because the processing has to be done, all the data involving in these, from all this data, and to form these auto and cross correlation matrix, all have to be at the central single processor, making it not distributed. I mean, for our sort of demonstration, that was okay, but it's not too realistic. Okay, but so in the next project, we use, as you know from your statistics course, maximum likelihood estimation is a very well-known statistical method. It's also known that it's optimum for large signal-to-noise ratios. And so we use the maximum likelihood method in the frequency domain for wideband signal direction of arrival, source localization, optimum sensor placement in the frequency domain. We had a paper in transactions on signal processing a few years ago. He was a PhD student, myself, and Ralph Hudson was a retired chief scientist. He was the aircraft working with me for many years. So the AML method generally outperforms the other known form of wideband music and other method. It has relatively high complexity. All maximum likelihood method essentially is a search method and has some high complexity, although we reduce the complexity to work actually on very small census processors, you'll see. Okay, here's a high-level pictures of a near-field data. So if you have a source coming out, the wavefront curve, 12U, and so the sensors, by finding not only the directions but also the curvature, can estimate both your directions and as well as your range. On the other hand, if you have a far field, so from where I am to the people in the middle of this room is already far field. For somebody who's in the very front row, maybe there's some near field effect, but certainly people in the back is far field. The wavefront that reaching you is almost a plane in front. In that case, the only thing you can do is find out directions, and you cannot find the range. So you have to use some other methods to find the range. And range in that case can be found by using, if you have two arrays, you know one of them giving you a given angle directions and the other one giving you another angle just by beam crossing, you can find out location. That's a standard method in RF, in radar processing. It's well known. Okay, so our algorithm, again, this is not the time to go into equations. Our signals obtained in the time domain, we perform actually a frequency domain, we do a FFT, and then we find the steering angle, and then we form the likelihood function. And then we actually literally search for the angle that match the result equations. We'll say more about this in a minute. No. This is not time to go through equations. Yes. Some medium level complexity processing problem. But instead of working with all possible frequency band, we work with biologists. Two kinds of birds. One's a woodpecker, bird that. You have woodpecker in China? Yes, you do, right? Woodpecker, yeah. Woodpeckers are animals that knock on the wood, right? Those are the woodpeckers. And the Mexican ant thrush, some bird. So this is the spectral property versus its amplitude in dB. So that you can tell, this is in dB, so that the woodpecker has actually only a few dominant signals of interest. The Mexican ant thrush actually essentially have just these things. These are many dB down. This is 0 dB, this is 15. So it's, so the significance is only. So by knowing that, we actually do not do blind arbitrary angle search over frequency band in these ranges that don't have any signal of interest. So we picked for the woodpecker, there's only these and this over here. Okay, this is just a high-level description. If you, in a near-field case, if you put the sensors here, you actually have a peak in them. what the sensor is. And then in the far field, you get the directions of At that time, we worked with Xerox PARC. As you may know, Xerox PARC was a wonderful organization funded by Xerox starting in the 1960s when Xerox had lots of money and didn't worry about that. Xerox PARC people invented the Ethernet, they invented the GUI, they invented essential single unit microprocessor computer in which Steve Jobs visited them and then essentially opened Apple. And I don't think Xerox ever made any money out of them. Xerox didn't care. So PARC was a wonderful place. By that time, this was in a few years ago, Xerox is not doing so well. They almost collapsed, as you may know. And so the PARC people had to go out independently, just like university people. So we were funded by the same type of project. So they were the hardware people, we were the algorithm people. This is in the semi-anechoic chamber, a room with some padded foam. These are different microphones. There's one big, ugly-looking green speaker in the middle of the room. The only thing Xerox about it was we use Xerox paper boxes sitting over here. If you look carefully, these are Xerox papers. That's the only thing about Xerox. Okay, so this is the room in which you have 6 microphones. This is using our new AML method. This is using our previous method. So let's see. So the square box is the sensor, the microphones. The circle is the actually source, the ugly-looking green speaker in the middle of the room. And this is our algorithm in locating where it is. So it's pretty good. And here is, it's not quite as good, but pretty good. Right, okay. Then, so this shows the RMS error for AML 73 centimeters, and this guy is 157. Okay, so we went outside to do this experiment. That's me, that's my PhD student, that's Jim Rush, and that's Han Cao, who's now, after Xerox thing, he went to Microsoft headquarters in Redmond, Washington. Now he's, I think, the number 2 guys at Microsoft lab in Beijing. Okay, so this is a road just outside the Xerox PARC building. And so Jim Risch is going to push this ugly-looking green speaker down the middle of this road. And so this is the middle of the road. So we have 3 microphone array, each one with 4 microphones, 4 linear array. And we do beam. So the red points are indicating the beamform, the result of a least square fit of the 3 beams coming from these 3 direction of arrival estimated from the 3 arrays. So, and you can tell in this region, it's quite good. As once you're outside the convex hall of the placement, then the result works. We have done analysis and showed that. So the AML algorithm does better, and then the first version algorithms gets worse, particularly outside the convex hall. Okay, the second project, well, as you know, all DARPA projects, those people really don't care about writing papers. In fact, DARPA project managers are perfectly happy if our students don't write a single paper. But if they're a PhD student, they have to write some papers, right, to graduate. DARPA people are big on demonstration, okay? So that project was a fairly large one with many different groups. We were associated with the Xerox PARC people. They built 3 sensors, sensor 1, 2, and 3. This is 29 palms. This is an aerial view. This is a desert in the Mojave Desert, halfway between Los Angeles and Las Vegas. It is a terribly hot, miserable place. And so they have some track vehicles, these half-track tanks with tracks in the front and wheels in the front and the tracks in the back, running back and forth doing experiments for a whole day. One of the sensors got run over by this track vehicle, so we actually had only 2 sensor arrays. Okay, and so this is the result. So these are the road to the best. So we only have 2 nodes here. So we only had 2 nodes. Thank goodness we had 2, right? You need the 2 cross beaming to get a localization. With one of them, you only get directions, right? With one of them, you only know this guy coming, the signal coming this way, but with this one coming this way and this one coming this way, you can get a. So we were able to locate the track vehicles as they move. The track guys move back and forth, and they did this thing for half a day. I was there for about 2 hours. I was dying with hay fever allergies, so I left as soon as I. But it worked, right? I mean, it worked out in the field, so people are happy. We worked with Deborah Estrand, who's actually one of your organizers in this conference, in a sense that's a NSF-funded project for 10 years, which is ending. She has very good connections, and she got a whole bunch of IPACs. IPACs are these early PEA stuff, which is nobody's using them since the smartphones does everything now. She got a whole bunch of these guys. With an iPad, has a built-in microphone, has a very, very low processing ARMS CPU unit. You can buy a unit in the back, give you 82.11b wireless card. So this thing is actually a little acoustic wireless sensor. So we got 4 of these guys putting on a table. So we have 4 of these guys here. So we can do actually applying our AML algorithm. So with a single source playing out of just a standard speakers you get from your laptop, standard desktop little speakers. So just a plain speaker playing some I think some music. So we're able to locate it, repeat this many times. Each black cross is one experiment. So with a single source, it does very well. We then have 2 sources. Then the first source we estimated quite well. The second source you can see the spread and not as good. Okay. Then SENSE being sponsored by National Science Foundation, which is a very different philosophy than the DARPA. But we do have review once a year. So the reviewer for this was Professor Bruce Hyatt from University of Illinois. Some guy I actually knew when he was undergraduate. Okay, so this is the back of engineering building, open area. We have 4 of these IMAX here forming a AML angle estimator. We put a speaker here, and we put another speaker there. And I will show you this. So this is not a simulation. This is the actual real-life data captured and put into a PowerPoint. I had 2 Italian visitors. There's a lady visitors, and I had a female, her boyfriend. He's a very good sort of real-time embedded system programmer who designed using these very, this is 6, 7, 8 years ago, ARMS processor, very low CPU capability to perform our AML algorithm in real time. And in the old version of PowerPoint it worked, but now I have a separate. So let me see what I can close this thing and give you a demo. I don't know about synchronization. What kind of PowerPoint is this? This is a new PowerPoint? Well, yes, there may be some synchronization. Trying out new things on new computers is very dangerous, right? In front of 50 people. Okay, I'm going to go to the full view. Oh, sorry, this is not the one. This is the second one right here. Okay. But then this one. Okay, we'll see how it works. What's that? Well, there's physical sound and then this guy detected. Now this are the same. This is the switch over. Okay. Then Professor Bruce Hayek said, we asked this young lady to move the stuff. We got this working the night before, and we have never tried this out. We were about to faint because. So, but his request was very reasonable. So we asked her, Noah, would you please just take the microphone and walk? And as you saw, this thing slowly moved over, and of course he saw, oh, that's very nice, and walked away. There's a whole bunch of other campus. But we looked at myself, the Phil, and Thomas, and other cases, looked at each other. We couldn't believe everything worked. Let me try again and see whether this time now you can. Supposed to play the sound first and then voice the other one. This is our system. Our system is not anti-causal. It doesn't predict it. So when I play this thing will point. Play the new. This points direction. And then we ask her to move. To start walking toward the middle. And see she moved. Naturally there was only about 1 second delay. And then when she reached the middle, it stopped. And Professor Hayek said, oh, that's very nice, and he went away. But we were shocked they worked. Okay, the second was if you have two of these guys. So that one is not a simulation, that's a measured data that's fed into PowerPoint. So this is where you stand in front of that building, you will see the same thing. This is just showing that with two units like this. So this guy will point here, this guy will point here, you can locate by this side. And this is done using just an ARM processor on these 10-year-old type iPad. These are the iPad that, who makes them? That company bought over by HP. And HP is so bad. Nobody, they didn't sell this anymore. Nobody buys this. Okay, so that was that experiment. Okay, let's go on. How do I get back to my slide? This is very Chinese control L. Good. All right, so when it was in the 4 years ago, PowerPoint, this will be integrating this because of okay. And these are details. We study about the inter-element spacing with various grading modes. So these are the different angles with different size for different birds, woodpeckers, and ant thrush. These are the gait patterns of the alpine forms. Various properties which we'll do. Okay. This is, again, actually a real-life measurement we did, showing that we can actually do active cancellations. So this is the time domain of a woodpecker waveform. This is a time domain of a dusty ember. This is the frequency domain of the woodpecker, and this is that of the ember. Okay. So the next figure is if you have a single microphone, both of these are equal distance, you see this guy. Two things gobbled up. We use a 8-element microphone array to do our AML algorithms. And we're able to separate them out, find out one source at 60 degrees and one source at 180 degrees. But not only that, we can actually cancel out the effect of this guy on the source from here, and cancel out the effect of this guy on the source from here. And we're able to reconstruct. So this is the separated signal for the woodpecker and its frequency domain. This is the time domain of the separated end burnings. If you just look at casually, this and this to this, they look very, very similar. They're not identical. And this is in an outdoor spacing on a Sunday morning in the central courtyard of our campus with no students. Normally it's a very busy place, Sunday and no students there. So this is actual, these results are measured results with an 8 microphone array. Okay, and then we also have used to study mammoths. Mammoths are ground squirrel who live in the ground. In this Rocky Mountain with another professor there. This is a terribly difficult place. You fly to Denver, you take a little airplane to a town, you don't remember, then you rent a car, you drive for another 2 hours in the middle of the Rocky Mountains. People have been doing biological field measurement for 30, 40 years. These professors have been keeping track of these guys for many generations. So the stuff we built at that time, a PhD student of Deborah Abstrand was a computer engineering student, built this unit. It's a fully wireless distributed system. It's self-contained. It can perform using ultrasonic transducers. It transmits a sequence of ultrasonic sound that can locate the locations of each box. And then they use our AML algorithm to do the direction of arrival for the source of interest. So it's a microphone array, omnidirectional speakers for the ultrasonic sound. And this is a different version. Now we are actually into version, this is version 1 a few years ago. Now we actually just finished version 4 box. Okay, so this is a top view of the Rocky Mountain Biological Laboratory. Okay, so this is a sort of map of the likelihood for various reasons. With only 4 microphones, you have actual, not a single 9-shot beam. You have side lobes in the beams because you only have 4 microphones. If you have 8, 12, then you can have shot single beam. But if you have just a single one like this thing, you're never sure whether the signal is coming from here, 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 or from this guy, you're not sure from here or here. But this guy, you're really not sure here and here. But if you have 1, 2, 3, 4, 5, 6 of these array, then this guy seems to tell you that you combine information, this guy from here, this guy 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 here, then you can estimate this. And this is distributed processing in the sense of these things are all sitting inside a single unit. So the processing is done distributed within each one of these boxes. And then you only need few bits of information to send to a central fusion center or controller, telling them the directions of this and this and so on. So this is, our AML is truly a distributed sensor processing system, which is more realistic. Because you don't want to take the raw data, transmit it over a radio system for it to do like our first system, which is interesting but really not practical. Okay, here's also a nice little demo. This is a spectrogram. So this is frequency versus time. So that here, and this shows our pseudo, shows this kind of thing. We have 1, 2, 3, 4, 5. I think we have 5 array of the kind like this stuff, sitting in the middle of in the middle of this place. So so here Mammoth is just a ground squirrel, makes very sharp single beep type sound, very sharp, which makes a very short duration, sharp, very broadband signal because it's narrow in the frequency at time and therefore broad in the frequency. So here, there's no signal, so these arrays are pointing in some random direction. Here, there is a signal, so literally these guys are pointing, and in this plot, the redder it is, the higher likelihood, the estimation. And then time goes on, it went over here, and these guys are random, and so it's blue. So this is a plot of spectrogram as a function of time, and a plot of the AML array gain patterns for the 5 wireless array nodes. And so the Mammoth course is present in the middle of the figure here. All DOAs are point toward the Mammoth, yielding for localization. The redness of the error indicates a greater likelihood for the second. Okay, so we had a paper in IPSN, which was held at MIT in 07. IPSN was held in Beijing about a month ago. So this is on MIT campus, we held this stuff, and you know, we did various demos, and it worked. Then I had a student working on the 3D AML. The previous result was only 2D, essentially only azimuth angles. But our bird colleagues, some birds do stay at different level of the trees, and they, for biological biocomplexity studies, they claim it's very important to be able to, different birds stay at different levels in the tree, so they want 3D. So I had a PhD, a lady graduate student from Iran, worked on the 3D part, and these are her equations. Okay. She used full, precise Kramer-Rao-Baum methods to find the best design for the placement. It turns out Deborah Estrin's computer engineering student, who's a very good engineer, he did it by intuitions, and his result, his intuitive design was very close to our optimized result. So here's a perfect example. Engineers with good insight, not necessarily having a full theory build system that's not necessarily worse than so-called the optimized system by people who write all the there are lots of equations about here, which you can see. So these are the different, Gerard is the Deborah student, modified is my student, Shamez Asghari result. First, okay, this is outside, coded, that's myself, we have somebody climb up on top of the building. To do measurements on elevation, you need to have those scores that are high up on the ground. So instead of just standing on the ground, we have somebody drop mic, a speaker stuff on this thing. And okay, so let's see which is which. The red are the true angle, the best we can estimate. This is Gerard's result, and this is her result. So true is supposed to be 90, his was 93, and hers was 89. I mean, slightly better, really, but nothing. Lou Gerard's result is really very good result. Okay, we went on to do 3D AML with 2 birds. This is a Mexican hen thrush, and this is another kind of hen bird, but it's a slight different. These are 2 different kind of birds. And Kramer-Rao-Baum indicating indeed at a high signal-noise ratio, our results are really quite good. Okay. And this showed the alternating projection of AML algorithm, which is really interesting. The alternating projection algorithm of AML method that was essentially, it forms a search algorithm. When there are 2 sources, it will do the best it can. And so this is a contour map of, these are actually the location of 2 sources. But the first time, both of them are not too accurate. In the second iteration, since you put you essentially know on this guy and only search over the second source and you do a better job. And then the third time you put a null on this guy and you search over this guy. So in fact, after 1 iteration, you get both of these guys very accurate. All right, so this is an iterative algorithm in which this is completely adapted automatically. We don't know what they are. So if you do the first iteration, you get both of them, you know, not too precise. Then put a null on this guy, you search over this, you get improvement. You put a null, you cancel this guy out, you search over this guy, you get a better one. So by that time, this and that is better than the original. We almost never need more than 2 iterations. And this stuff is pretty fast. So that's really pretty good. Okay, we use particle filtering. If you into the tracking business, you know, common filtering came into existence about 40 years ago. And then there was also linear common filtering stuff, which is really a linearized version of common. A true linear common filtering is just computation too costly. Particle filtering came into existence about 10 years ago, but has been used extensively the last 5 years. It has all the advantage of, for practical purpose of linear common filtering, except this is practical. Okay, I had a PhD student. This is only a small part of his work. This is our conference room that we become a conference room with some chairs. So we taped 4 microphones on the front of the room, side of the room, side of the room. We had a given student walking. So this is our x direction, y direction. So walking this way, x is always 0, and y is increasing. Try to have a person walk, you know, constant walking as a function of time. So this is a tracking result in x direction, so it's supposed to be 0. Right? And then this is the y as a function of time. If you just use a single snapshot of AML algorithm, you get these green-looking things with very wide variations with a single snapshot. But with using particle filtering, we're able to get this blue result, which is, you know, because it's smoothing out over result. A tracker is just not an isolated single snapshot. So we get this stuff. It's not perfect. This is only a very cheap experiment that it went out in there. If we work harder, we could do it. But this is y, and this is time. So that in theory, the red one is the ground truth, it's supposed to be linear. So again, if you just have a single snapshot of the AML, not so great, right? But if you use the particle filtering, it's sort of this thing. There's some bias, but just shows that particle filtering, using AML as an input to the particle filtering algorithm, you know, give you reasonable result. It will be really interesting because we can work harder. Okay, so more recently we actually use another method. I don't have any slides, but just time is almost up, that's fine. Using random set theory, a method we learned a few years ago. In probability theory, you have random variables and you have a collection of random variables forming random vectors. But those random variables are real value numbers, right? Real numbers. In random set theory, your elements are actually sets. And this is not our concept. It's actually formulated by very abstract French mathematicians in the 1960s. It was proposed by someone working in the tracking areas about 1970s, aerospace engineers, by the Ron Muller. His motivation was actually in the 70s. His project was trying to track multiple targets coming out of Soviet MIRVs, if you remember, MIRVs in the 70s. Okay, we use that to track birds and so forth. We don't have business to work with data. We only have birds, and the reason why we like random set theory is this allows in the tracking business to have 0 target, no source. So instead of having a separate method in which you first find the number of source and then you track it. So that's a 2 separate optimization. In optimization theory, if you do 2 subcase, then it's always suboptimal. You want to do the optimization in which you look for the number of source and track it as a single objective. And random set theory allows you to do that. Except the mathematics is very complicated. Random set theory is not something we normally learn or teach in probability course. And I have students work on that stuff. And, okay, so summarizing acoustic beamforming practical wireless sensor network. In our early experiments, we had terrible battery constraint problem. Before we know it, after 1 hour out in the field, our batteries are gone. In the early days, we went out to working with Rockwell science people. 1 hour in the hot sun, it's gone. And then so we sent students out to buy batteries. Those of you from America knows Radio Shack. Somebody said, oh, no problem. There's a Radio Shack only 10 miles away. Well, he went away for an hour and a half. We were sitting in the hot sun. So battery is a major problem. Everyone was a cell phone. No, the fancier the cell phone, the more frequently the charges. The same problem. We have low data rate transmission capability, not really suitable for central processing. So you want to do your local processing system, which is what we did in the AML system. The first system, all the data has to be transmitted to the central processor to do the joint, auto, and cross correlation, which is nice to talk about, nice to do these simple things, but you really would propose this thing to do for a real system. But the second system we built and it will work on the field, and that's great. If you have your R propagation near the ground, we and others have also studied this problem, is very different than when you have. That's the reason why your cell base station are high up, right? The lower it is, the more propagation problem. If you close to the ground, the propagation loss is 1 over R to the 4th, so it's really bad. Then you have, if you do sensor activation problem, multi-hop routing challenges, which many more people here work on from papers of tomorrow and the workshop, lots of these things, which are all very challenging. To get them to work in a real-life system with multi-hop is really, it's nice to write papers, nice to get money to do research and to build experimental system. Whether you really want the system to work out in an unknown real-life environment, it's another issue. Then you will need to have a standalone sensor network system involving self-adaptive and self-learning, all these things which are part of still active research. So, conclusion, we introduced wide and acoustic beamforming, the whole concept. We presented 6 projects of experience in using acoustic beamforming. The AML beamforming algorithm can be used for detection, localization, source separations, and tracking. And that has been used for hearing aid, there are already commercial products for teleconference in which you have a camera steered all the given speakers. It's well known. In a conference, it makes the other side much easier if you can look at the face of the one who's speaking, because when you say something, just smile a little bit, you nod your head. This is important, versus just blindly, you don't have that information. Some people do that. For us, there are vehicles, personal detections, tracking multiple animal source separation. And we thank all the different funding agencies. We work with Professor Taylor, Professor Boomstein in the Biocomplexity Department, Dr. Ralph Hudson, the retired chief scientist on ESL Raytheon, a wonderfully brilliant former PhD student, Lou Gerard, Deborah student. Many, I had about 12, 14 PhD students, and other people who work with these people. And we have to thank the birds and the animals making the sound. Thank you.
Very interesting talk. I guess you guys have lots of fun playing with birds, climbing up the roof. We have time for a few questions. Any questions from the audience? Maybe let me start. Okay, I'm not gonna falling down. So I know a lot of us here actually works in the MAC layer and above. Every time when we talk about physical layer, we kind of enter this semi-panic mode, say, this is not my domain, I want to stay away. Physical layer guy, I don't know how to talk to you. So the first question I have is, what is your suggestion to us live on the upper floor?
The upper level sets up a Mac and Well, you do have to remember, you must have some data and source of interest to use your system, right? And I'm the guy at the physical layer. I'm the guy who does the thing. Then our data gets feed into the system to go to multi-hop to do all these things. If you ever have to build a system, you need to work with it. You also need a hardware. I think many of the people who work at non-hardware guys either. Most of the people. I think most of the people, at least some quickly from the programs of with papers of non-hardware people. At least most of them. I'm sure there's some. But I can assure you, there's a big difference between writing a paper. When we went through this evolution, we first on our this generalized eigenvalue problem, we showed it to people, people with some real life experience. Well, that's only a bunch of equations, and I believe you. I mean, bunch of equations. Maybe it's true, maybe it's not. Then we said, okay. So then we wrote the MATLAB simulations to show people it works in MATLAB. This is always a simulation. Simulation you can fool around. Not intentional dishonest, but I mean, you can put in all sorts of things that sort of working on simulations. Okay, we said, now then we have to breadboard stuff. Once we breadboard stuff, they said, well, that's only experimental system, how long does your battery last, how long is your radio propagation problem, if you have multi-hop and sort of how to work. Now, these problems, these challenges keep on going up. And if you have to build a system, depending on your funding source. Some are happy with just equations, others are happy with MATLAB, others are happy with experimental breadboard system. Others actually want a system that they can take back and use. And if it's a commercial product, they have to worry about the cost of building the system. So the answer to that is every level, every aspect of the problem is important.
Yeah, of course. I'm sure physical layer is important.
Sure.
So my question is about the timing synchronization.
Oh, yes.
Level of timing synchronization needed across nodes to produce
Good.
those.
There are two issues. For our AML, since it's sitting or connected to a central processor, there is essentially no time. But we also have, in some other system, was on the iPad and so forth, to do joint, we actually worry about synchronization within the system. In some of our papers, we actually, I guess I myself, our student have, but Deborah Aswin's student have, Jeremy Elson has written some very clever papers on synchronization. And more recently, since we have a Swiss student, Benjamin Schmidt, who actually has some very profound method to synchronize things. If you're interested in offline, I can give you information. Yeah, synchronization is a big thing. Absolutely, we agree. I guess you're interested in some aspect of your problem. Without synchronization, you cannot do coherent beamforming. Absolutely. Also, I'm happy to take questions in Chinese. I left China when I was 10 years old, but I can understand some simple Chinese. I definitely cannot answer you in Chinese. So English or Chinese, either question is okay.
I can speak English.
Okay, fine.
Yeah, I'm quite interested in that you mentioned you use random set theory.
Yes.
And I want you to tell us more about the progress in this direction and what's the biggest challenge you think?
Okay, the biggest challenge is to, you need a very solid math background. You need equivalent to a first-year graduate student math background to be able to read the It's measuring theoretic stuff. So you must have taken a graduate, a senior math and first-year graduate student measure theory course and probability in measure theory setting. Okay. And second, the best book to buy is Muller's book, this thick by Architect. It's about $180, this thick. books are terribly expensive, and these architect books are just outrageous. But fortunately, Muller has written many tutorial papers. So Muller, spelled M-A-H-L-E-R, Ron, his first name. You can go to Inspect and type in random set theory Muller, and you can get half a dozen tutorial papers by him and so forth. They're all very difficult to read. But sure, if you're a PhD student looking for something new to do, that's a perfectly wonderful thing. We have some papers which we sent you. Our papers are relatively simple-minded, but I would say my students understand much more than I do. I've invested a fair amount of time, but by no means I'm not ready to take an exam on random set theory. It's very complicated stuff. But that's what students looking for PhD stuff to do. Ron Muller is very motivated. We actually, Ron Muller can be very nasty too. Accuse other people using conventional tracking theory. People is being dumb. Only he's smart. So he was a session chairman. My student and I had a paper. I wasn't able to go. So I told my student, be careful, this guy. But he was very nice. He's very glad that people are trying out his method to do some simple-minded. We have some bird data. And he said, great, you guys are using tracking his method for birds and so
on. Unfortunately, we don't have much time. And let's take a break. Before that, I want to announce a few things. First of all is all the presentation will be recorded on tape. So if for some reason you don't want the tape to be available online, please let us know. Otherwise, by default, we'll put them online. And then the second thing is we'd like to have a group picture. So if we can gather now in front of the big door, we'll take a snapshot, and then you can drink your coffee, have your late breakfast, and set up next session.
Yeah, he was there. His group also he was also a member of the group that funded by
Yeah.
Oh, you have this in there? Oh, curious. They need this. Energy is but I think our stuff is more precise. I'm familiar with his stuff. I end up with his stuff. Okay, so anyway,
Yeah.
that's the one. So you overlap. Yes. I see. I see. Oh, okay, very nice.
So I came back and actually my professor in China. He is a target tracking.
I see. Okay. Okay. Multiple target tracking.
Right.
Okay. Well, then
That's
you.
our own, and they have to.
They have
Actually, yeah, it's some recent things that they're want to do. And yeah, so that's why I'm very but I'm doing the big sort of localization. I came back and I prefer to do yeah,
Sure.
that's all.
Our stuff was either a acoustic source or no source. So in the random set, it allows you to have a framework which allows you random set will allow you empty set, which is which is no target. So yeah. And which, as I said, with theoretically optimization, you don't do two suboptimal selections. You don't say you have 3 targets, and then you that's 3 targets. Because that's traditional. That's a traditional. That's a round molar approach. No. Oh yeah. Round molar was straight up. Round molar was straight up. I don't know. He works at now it's public, but in the old days was some other, I think it was Honeywell. He had some one missile came out, and then you put out 20. Some are real dumb, and others are dummy. So you want to track them to determine which one is real, which one is just a dummy.
Yeah.
And of course, the dummy ones are not the same weight as other ones, so their properties are different.
Yeah.
But then initially, you have to track them for parts before you can.
Right.
The real ones and the dummies don't move for the same dynamic because they're lighter and so. But you see, I have to track them.
Right.
So that was this motivation. Yeah, some of them are actually reasonably easy to read compared to this book. This book is very difficult.
Yeah.
And then the real thing is the French mathematician. It's very abstract. Well, French mathematicians are abstract by definition. They never work on one dimension when you can do multi-dimension. You never work on finite dimension when you work with different dimensions. Why work on 3D space when you work on Hilbert space? Why work on Hilbert space when you go to finite space? When you go to homological space? Even French engineering students learn abstract mathematics. They sometimes get too abstract than for their own. I think of it, I'm an engineer.
Yeah.
I learned only the math necessary to do my job. Not any more than necessary.
Yeah.
I mean, I went to graduate school in Princeton, which we spent a large amount of time learning the language.
Yeah.
We actually went further to real life engineering. Fundamentally, I mean, I'm still not retired. I enjoy what I'm doing because I was there for my training. Otherwise, that's good advice to young people. If you really want to stay in the research business.
杨老师，我们需要用拍照片吗？
好，不过 OK，sorry， OK， 好 ，OK， 需要。I'm coming。
快点，没关系，快点，没事。
快，来，好 ，OK。Well, I carry my computer with I know. Oh, be careful. So and then 我们在 UCLA 的时候，我发现也没关门。
你们俩干嘛呢？上厕所去。